Good day learners. In this video, we will be discussing about how to determine the loop gain with the stability problem and the Nyquist plot. So, we will discuss about how to determine the loop gain. So, this loop gain is given as A beta. So, it plays a major important parameter in the feedback amplifier. This loop gain is going to be the deciding factor about the feedback amplifier is stable or unstable. So we will discuss about the way to derive A beta. So this first diagram is going to indicate the general feedback amplifier we have discussed already. This is going to be the source and load here, and we have the gain with respect to the amplifier. And the second diagram is the basic feedback amplifier with loop broken. See here, the loop is broken here at the amplifier input. This is going to be the amplifier input and this is broken over here. So to find out the loop gain, what are all the things we are going to consider is, we are going to consider that source, here is the source. We are going to consider this is going to be a 0 and break the feedback loop. We have already broken it. You can see in this figure. And we are going to apply a test signal called as xt. So we have broken this input signal and we are going to apply a test signal called as xt. So A beta is given as minus xr by xt. So this is going to be our first equation. So after this, what we are going to consider is the feedback amplifier before, how it is going to react, and after broken, how the feedback amplifier is present is given here. See here, we have the amplifier and beta, and after broken, we have the input resistance here with respect to your resistance voltage. So in the next step, we are going to see this VT is going to be the voltage applied to the right hand side terminals, and Rn is going to be the left hand side resistance terminals. The second equation is followed by the first equation we saw with respect to our test signal, and here it is respect to the voltage, and the third equation is with respect to current. So now you can see the diagram here. This diagram indicates the feedback loop with respect to your op-amp. Actually, it has this. When we draw this, this becomes an op-amp for you. Okay. So how we are going to find out the resistance voltages? It is going to be with respect to your gains, where the test voltage is applied to the right hand side terminals, and with respect to that we are going to calculate the loop gain. So our final equation for loop gain is going to be A beta, which is given as minus VR by VT or minus VR by VD. Now we are going to see the significance of poles, zeros and feedback loop. So system poles is going to be the major thing which acts as the root of the denominator h of s, which is going to be the transfer function. The system zeros is going to be the root of the numerator of h of s, and the system natural modes is going to be the time function corresponding to the poles. So whenever we are going to plot, we have two main parameters. One is going to be the poles and other one is going to be the zeros. So what is poles? Here we are going to see the poles as, we are going to have the external excitation to set to be 0, and the poles are always independent of the external excitation. Though we excite things, it is going to not be dependent, rather it is going to be independent. And this poles is actually depends only on the feedback loop. What about the transmission zeros? This transmission zeros is going to depend on how and where the input signal is applied to the loop. So zeros are always focused on the input signal, and poles are always depends upon the feedback loop. Now we will discuss about the stability problem. Then stability problem, we have a closed loop transfer function for the feedback amplifier, and this is given as AF. So here if you see, this is going to be the closed loop transfer function, where A becomes the open loop transfer function and beta, as usual, it is going to be the feedback transfer function. The components and parameters for this particular amplifier changes with respect to frequency, because Open loop gain is always going to be a function of frequency. Now, the closed loop transfer function is followed by the AF. We are going to find out this loop gain in terms of TS. So what is this j omega is? It is going to be the imaginary value. So how this imaginary value gives us the frequency at which the phase angle becomes 180 degree, then the loop gain will be a real number with a negative sign. See here, when the frequency is, this is going to be a frequency. When this particular phase angle is going to be 180 degree, then the loop gain is going to be the real number with negative sign. And the magnitude of the loop gain is going to be unity when this Tj omega is going to be -1. And the frequency of the feedback is going to be always positive. When this TJW is going to be -1 in terms of negative, the closed loop gain becomes infinity. Hence, the amplifier output is going to be based on the zero input. That is, even with the zero input, the amplifier is going to give an output and which acts as an oscillator. The next topic what we are going to discuss, followed by the stability problem, is going to be the Nyquist plot. So in this is going to be the diagram for the Nyquist plot. Actually, this is going to where we are going to test the stability of the feedback amplifier. So the Nyquist plot determines whether the system is stable, and with that it is going to give the degree of the system stability. So the criterion for the Nyquist is that amplifier is unstable if the curve encloses the figure -1 plus j0. This factor is going to be the curve encloses at this particular point. It indicates that it is unstable, and the amplifier is stable if the curve does not close at this particular point. So this diagram is going to be the locus of 1 plus a beta at the value when it is going to be equal to 1. So it is a circle of unit radius. See here, it has the radius to be 1, that is unity, and with the center of -1 plus j0. So it slowly, the a beta extends outside of the circle, and the feedback is negative when this 1 plus a beta is greater than 1. So it slowly extends outside. So when it lies inside, this 1 plus a beta is going to be less than 1. So then the feedback is going to be called as a positive feedback. See here, this particular go is going to be called as a positive feedback, and when slowly it goes outside, then it will be the negative feedback. So the last diagram is going to be showing the stability condition based on the Nyquist criterion. This is just an example where you can see the first one is going to be stable. See here, it is stable and it does not enclose at -1 plus j0 point, whereas the locus shown here, it is actually enclosed and it is unstable.